All right, so let's say you're deep in SOLIDWORKS, right? And you're working on this like crazy huge assembly. It's got tons of parts, and it feels like every time you even try to open the thing, you've got time to make a coffee, do some laundry, maybe even write a novel before it finally decides to show up on your screen.
Yeah, I can definitely see how that would get old pretty fast.
Yeah, and then forget about rebuilds. Those take forever. And trying to get your team to collaborate on it, it's more like a digital traffic jam than actual teamwork.
It sounds like a classic case of large assembly woes. And trust me, you are far from alone in that struggle. A lot of SOLIDWORKS users out there are wrestling with those same painful slowdowns. I mean, we're talking about the long open times, the rebuilds that seem to last an eternity, the lag you get just trying to switch between different configurations, or even just moving between windows. It's enough to make anyone pull their hair out.
Totally. And it gets even worse when you try to deal with the drawings for these massive assemblies. Just trying to open them, update the views, or even switch between sheets feels like you're wading through molasses. And don't even get me started on saving. Sometimes it feels like you're just crossing your fingers and hoping it manages to finish before your next meeting starts.
Absolutely. It can be a real nightmare.
Which is exactly why we're doing this deep dive today. We're going to dig into some really cool strategies for designing faster and smarter, especially when it comes to team-based design in those massive SOLIDWORKS assemblies that we all love to hate.
We're going to be drawing insights from a super informative presentation called 1221 Large Assembly Collaboration Masterclass, Faster Team-Based Design. It's a real treasure trove of knowledge, and it features some serious SOLIDWORKS expertise from Ellen Vargatu, who's with Trimix Solutions.
And we also get insights from Don Ganya, who's a senior design leader and the SOLIDWORKS administrator at EMS Tech Inc.
EMS Tech is a pretty interesting company. They specialize in bulk material handling systems, so, those really heavy-duty machines you see at ports, mines, all those places that move mountains, literally.
Yeah, they've been around since 1988. They've got over 100 employees globally. Their vision is to be a real leader in the bulk material handling world, focusing on innovative and really customer-driven solutions. And Dawn has been with them since 1998, so she's been a huge part of their success in using SOLIDWORKS.
For sure.
So our mission today is to take all the amazing stuff that Alan and Dawn shared in their masterclass and distill it down into some super practical takeaways that you can use. Yeah, you, the person listening right now. Because we want to help you conquer those frustrating slowdowns and collaborate like a pro, even when you're facing the most gigantic SOLIDWORKS assemblies imaginable.
That's right.
Okay, so let's get real for a second. When you're dealing with these performance issues in SOLIDWORKS, trying to figure out what's actually causing them can be incredibly frustrating.
Oh, yeah, I hear that.
It's like searching for a needle in a haystack. There are just so many potential culprits. The presentation we mentioned actually laid out a ton of factors that can contribute to these slowdowns.
That's a pretty long list.
It really is. Let's see, we've got slow media, so maybe your hard drive is slowing you down. Then there's the graphics triangles, older file versions that might not have been updated properly. And then you have those super complex flexible assemblies.
Yeah, those can be real resource hogs.
Oh, and then you have things like missing body data, which might not even realize is causing problems.
Right. We can't forget about high image quality settings. While they might make your model look amazing on screen, they can really tank your performance. And then there's the equation bugs, the in-context references that can get super messy and span the entire assembly. Even the sheer number of bodies in your parts and assemblies can make things really sluggish.
It really adds up.
Yeah. And let's not leave out all those section views. Having tons of those active can definitely contribute to things slowing down. And then there are the product flexible assemblies, the cosmetic threads, the multiple configurations. I mean, the list just goes on and on.
Yeah, you're not kidding. There's topological errors in your geometry, the limits of your computer's hardware, users who haven't been trained properly and might not be following best practices. And then there are the hidden features lurking in the background, dual drivers of dimensions causing conflicts. Even something as basic as corrupted files can throw a wrench in the works. And unoptimized system settings can make a big difference too.
And let's not forget imported geometry, which can sometimes come with a ton of hidden data that can really bog things down. The way you open the assembly, like whether you use lightweight mode or resolve everything, can make a huge difference in load times.
Oh, for sure.
And then you've got circular references, creating those annoying dependency loops, and even your external reference settings can impact things.
It's mind-boggling when you consider all of the different things that can go wrong.
It really is.
But the masterclass did a good job of breaking it down into 3 key areas. They called them the 3 critical factors for maximum speed in SOLIDWORKS. They use this great rutzing analogy to make it easier to understand.
Oh, yeah, that's a good one.
It's like this. Think of the racing track as your workstation, so your computer hardware, right? And the racing car is SOLIDWORKS itself, the software you're using. And finally, the racing driver, the one who's actually controlling everything, is the user.
In other words, it's all about how you work with the software?
Exactly. You can have the fastest computer and the most up-to-date software, but if you don't have good work habits, you're not going to be winning any races.
You're going to be stuck at the starting line.
Exactly. So knowing all these things, where do we even start? How do we begin to tackle these performance issues?
Well, the masterclass actually laid out this ideal agenda for a 22-hour training course. Can you believe that?
22 hours.
Yeah. But obviously, we don't have that kind of time today. But even just taking a quick look at this agenda can give you a good overview of all the areas you should think about optimizing. It's broken down into 8 really key modules.
Let's go through them.
All right, so the first module is all about taking a peek under the hood, so to speak, and understanding how SOLIDWORKS actually processes assemblies. Because if you know why certain things cause slowdowns, you're in a much better position to fix them.
Makes sense.
The second module is about phase analysis. It's basically a divide and conquer approach to figure out where those major time sinks are happening when you're working on an assembly. Then there's environment optimization. That's all about where you store your files, system options, your templates, even how you've set up your user interface. All those little things can add up.
Right. So you're making sure SOLIDWORKS is running as smoothly as possible.
Exactly. Then module 4 is a really interesting one. It's called Freedom to Design with Consistent IQ Before Saving Files. And it really emphasizes how important it is to manage the level of detail that you're actually working with before you hit that save button. That way you avoid unnecessary processing later on.
That's a great tip.
And then there's analysis tools. This module covers all the built-in features in SOLIDWORKS that can help you diagnose those performance issues we've been talking about.
Cool. So SOLIDWORKS actually gives you the tools to figure out what's going wrong.
It does. It's pretty handy. The next 2 modules focus on optimization at different levels. So you've got part-level optimization, where you look at how individual parts are designed and put together. And then you've got assembly-level optimization, which deals with how those parts are combined and constrained within the larger assembly.
It makes sense to optimize at both levels.
Definitely. And finally, we get to the 8th module, which is the one we're going to spend most of our time on today. It's called Team-Level Collaboration for Large Assemblies.
Okay, so now we're getting to the good stuff.
We are. Because even if you've got your individual performance dialed in, once you start adding multiple people working on different parts of the same massive assembly, that's when things can get really hairy.
Oh, yeah. That's when the real fun begins.
Exactly.
So let's talk about that. What kind of chaos can we expect when we have multiple users and one assembly?
Buckle up, because it's going to be a bumpy ride. I mean, for starters, you've got the potential for circular references. That's when 2 or more components become dependent on each other, creating this infinite loop.
And I'm guessing that's not a good thing.
It's definitely not ideal. It can make your assemblies super unstable and slow down rebuild times like you wouldn't believe.
Ouch.
Yeah. And then you have those really heavy referenced models. Like, let's say one user has this incredibly detailed subassembly, but another user only needs to reference a tiny piece of it for their work. If they try to load that entire subassembly, it can really bog down their system. Plus, there's the whole issue of who's responsible for what. That can get confusing really fast and lead to people duplicating work or having to redo things.
Yeah, and then you've got all the errors and warnings popping up, and those little rebuild icons that just stare at you from the feature tree.
Oh yeah, those are the worst. They just mock you.
They really do.
The masterclass really highlighted the problem of excess referenced data in subassemblies and this idea of data ownership at the team level.
Okay, so how about we try to visualize this?
Mm-hmm.
Imagine you have user #1, and they're the owner of subassembly A, meaning they're responsible for designing and making any changes to it. And then you have user #2, who needs to work on subassembly B. But here's the thing. Subassembly B needs some specific references from subassembly A. It could be anything, maybe the location of some mounting points or the overall shape.
Got it. So they need to work together.
They do. But traditionally, what would happen is user #2 would just insert the entire subassembly A into their assembly. The problem is user #2 probably only needs a tiny fraction of the information in subassembly A, so loading the whole thing is just a waste of resources.
It's like trying to fit an elephant into a shoebox.
Exactly. Plus, user #2 might only be able to open subassembly A in read-only mode if user #1 is still working on it. And even worse, Any little change that user hashtag 1 makes to subassembly A can trigger this massive rebuild in user hashtag 2's subassembly B, which is super annoying and time-consuming.
That's definitely not efficient.
So in this kind of situation, what are we actually trying to achieve? The masterclass outlined 3 main goals for successful team collaboration on these huge assemblies.
The first goal is to free user hashtag 1 from having to constantly worry about how their changes to subassembly A are going to impact everyone else downstream. They should be able to focus on their design without having to second-guess every single move.
Right, because that can really stifle creativity.
Totally. The second goal is to cut down on all those unnecessary rebuilds in subassembly B. Like, user hashtag 2 shouldn't have to wait for their entire assembly to rebuild just because user hashtag 1 tweaks something in subassembly A that doesn't even affect B.
It's all about working smarter, not harder.
Exactly. And the third goal is to give user hashtag 2 more control. They should be able to decide when subassembly B rebuilds to incorporate changes from subassembly A. That way, they can avoid those unexpected disruptions and keep their workflow moving smoothly.
It's all about control.
Exactly. So the question is, how do we actually achieve these goals? And this is where the masterclass gets really interesting. They came up with this really cool solution, and it's all about building connectors in a dummy assembly. Basically, you create a lightweight bridge between the 2 subassemblies that only contains the essential information user hashtag 2 needs from user hashtag 1's work.
I'm intrigued. Tell me more about these connectors.
Okay, so here's how it works. User hashtag 2, who needs the references from subassembly A, starts by inserting assembly A into a brand new assembly that they own. This new assembly is just a container for the connector. And because they only need it for reference, they can often load it in a lightweight or read-only state, which saves a lot of resource.
Okay, so it's not fully loaded.
Right, and here's the clever part. User hashtag 2 creates a separate, really simple connector assembly. We can call it assembly C. Inside this connector assembly, they create a basic part, which we'll call A. The key is that user hashtag 2 then takes only the relevant references they need from the read-only assembly A and puts them into this simple part A.
So part A becomes like a mini stripped-down version of the parts of subassembly A that user hashtag 2 needs.
You got it. It's like a cheat sheet. And because user hashtag 2 owns part A and the connector assembly C, they can reference it in their own subassembly B without having to load the entire subassembly A. That gives them the control we were talking about.
Like a backdoor pass.
Kind of, yeah. Now, the masterclass actually laid out 4 different ways to create these connectors, each with its own pros and cons. The first one is the 3D sketch connector, and it's been around since SOLIDWORKS 2000.
Wow, that's ancient history in the software world.
It is, but it still works. And the great thing about it is that it's super lightweight, it doesn't take up much space at all, and it's really easy to fix if something goes wrong with the references. The downside is that setting it up can be a little tedious.
Okay, so walk me through how to create one of these 3D sketch connectors.
All right, so user hashtag 2 starts by inserting user hashtag 1's assembly A into a new assembly that they own, like we talked about before. This is going to be the home for our connector. Then, at the very center of this new assembly, user hashtag 2 adds a new part.
And what do they call this new part?
Well, it's important to give it a name that makes sense, like assembly a connector, and make sure it's saved as a separate file.
Okay, so this new part is where the actual connection magic happens.
Exactly. So then user hashtag 2 goes into this new part and starts a 3D sketch. They basically use the different sketch tools to trace the edges or curves from assembly A that are important for subassembly B. Like if they need to know where certain holes are, they trace the edges of those holes in the 3D sketch. Once they've got all the references they need, they name the 3D sketch something clear, like reference.
Reference, got it.
Right, and they can even give it a color so it's easy to see. Then they go back to the connector assembly. The next important step is to save and close the connector assembly. Then user hashtag 2 opens the assembly A connector part all by itself and locks the external references. This is super important because it stops the connector part from automatically updating if user hashtag 1 makes changes to assembly A. User hashtag 2 wants to be in control of when those updates happen.
So they're freezing it in time.
Pretty much. So after locking the references, they save and close the connector part again. And then finally, when they're working on subassembly B, they insert this assembly A connector part into it. And the last step is to make the assembly A connector an envelope component. That tells SOLIDWORKS that this part is just for reference and shouldn't be included in things like the bill of materials or the mass properties of the whole assembly. User #2 can even add the reference 3D sketch to their favorites folder if they want to find it quickly.
That's pretty slick.
It is, right. And the presentation actually gave a shout out to Matt Lombard for really highlighting how powerful and efficient a simple 3D sketch can be when you're working with assemblies.
Okay, so what's the next connector option?
The second one is called Envelope Publisher, and it came out in SOLIDWORKS 2020.
Okay, so how is Envelope Publisher different from the 3D sketch connector method?
Well, Envelope Publisher is generally easier to use and set up, and it's more robust. But the big catch is that it only works with components, not individual bodies. So if you're working with weldments, for example, and you need to reference specific parts of them, you're out of luck.
Okay, so it's got its limitations.
It does, but it can still be really useful.
So how do you use Envelope Publisher?
Well, just like with the 3D sketch method, user #2 starts by inserting assembly A into a new assembly that they own. Then they add a new subassembly at the center of this new assembly, and this is going to be their assembly A connector. They give it a name that makes sense, just like before, and they save it as an external file.
So instead of a part, you're using a subassembly this time.
You got it. And then they use the Envelope Publisher command. They choose all the components from assembly A that they need to reference in subassembly B, and then they set their new subassembly, the assembly A connector, as the destination for those references. They add a group in Envelope Publisher, and then close the tool. And finally, they save and close all the files.
And what happens when they open the assembly A connector subassembly?
Only the components that were selected in Envelope Publisher will be loaded into that subassembly, so it's a much lighter weight version of assembly A. But like we said, the big limitation is that it works with whole components. If you only need a small piece of a multi-body part or a weldment, you can't just pick that piece with Envelope Publisher.
That's good to know.
It is.
Okay, so what's next? What's the third option?
The third option is called Make Multi-Body, and this one came out in SOLIDWORKS 2024. It gives you a lot of control over updates.
Make multi-body, huh? That sounds interesting. What's the process like?
Okay, so this one is a bit different. User #2 starts by inserting assembly A into a new assembly, just like before, and they save it. But then at the assembly level, they start a 2D sketch.
A 2D sketch.
Yeah, the idea is to draw a closed shape, like a circle or a rectangle, that covers the area of assembly A where the references they need are.
So they're basically drawing a box around what they need.
Exactly. And once they've got that shape, they do an extrude cut through all outside of that shape. This gets rid of all the parts of assembly A that they don't need, visually at least.
Okay, so now they're starting to isolate the important geometry.
Right. And then they use the Make Multi-Body Part command. This takes all the remaining solid bodies from the trimmed assembly A and combines them into a single part with multiple bodies. And then, super important, user #2 locks the external references in this new multi-body part. Just like with the 3D sketch method, this gives them complete control over when and if this part updates based on any changes to the original assembly A.
That makes sense. So they're not at the mercy of user #1's updates anymore.
Exactly. But there's one thing to watch out for with this method. The presentation warned that if the original assembly A has a ton of different colors and textures applied to its surfaces, converting it to a multi-body part can sometimes slow things down because there's just so much graphical data that needs to be processed.
It's like those face-level appearances are adding extra weight.
Yeah, they are. But don't worry, the masterclass also gave a strategy they called ultimate optimization to deal with this.
Ultimate optimization. Lay it on me.
All right, so the first step is to get rid of all the display states in the new multi-body part. That's an easy way to get rid of all those colors and textures that might be causing problems.
Out with the old, in with the new.
Exactly. And then you apply a single color or appearance to all the bodies in the multi-body part that you actually need to reference. This basically creates a selection set. Then you choose this color, which automatically selects all the relevant bodies, and you use the Keep Bodies feature. This drastically reduces the number of bodies in the part. They actually had an example where they reduced the number of bodies by a factor of 30.
30 times fewer bodies.
30 times, yeah. And once you've got the body count down, you can delete that temporary color. The next step is to use the Defeature Simplify command with all the default options. This automatically removes any little details that aren't important for the overall shape and size of the part. And when you're doing this, make sure you choose the options to save as a new document and link to original. This creates a super lightweight version of the connector part while still keeping a connection to the original multi-body part in case you need to update it later. And finally, you lock all the external references in this new simplified part.
Okay, so what does all of this optimization actually get you?
Well, the results can be pretty amazing. The new simplified part opens super fast. Like in their example, it only took 4 seconds. And when user #2 adds this part to their assembly B, it loads almost instantly, like in a second or two. Plus, because the references are locked, they have total control over when and if they want to update it based on any changes that user #1 makes.
That sounds like a huge time saver.
It really is.
So that covers the make multi-body method. What's the fourth and final option?
The last one is called Local Speed Pack, and it's a pretty new feature. It came out in SOLIDWORKS 2025.
I've heard of Speed Pack, but Local Speed Pack sounds different. What's the deal with that?
So with Local Speed Pack, you actually start the process in user #2's assembly B. User #2 uses the insert speed pack instance command and chooses user #1's assembly A. Then they get a window where they can pick the specific bodies, sketches, planes, coordinate systems, or axes from assembly A that they need to reference. Once they've made their selections, SOLIDWORKS creates a local speed pack configuration of assembly A right inside assembly B.
So instead of creating a whole new part or sub-assembly, the Speed Pack is just part of user #2's assembly.
You got it. The cool thing about Speed Pack is that it keeps all the exact geometric information of the parts you selected, but makes everything else in assembly a super lightweight. So user #2 gets the references they need without having to load all the detailed geometry of assembly A. And just like with the other methods, they have control over when those updates from the original assembly A are incorporated into their local speed pack.
So it's the best of both worlds.
Pretty much. Now, they did mention that there is one potential drawback to using regular speed packs, and it probably applies to local speed packs as well. It usually means that any drawings you make of the speed pack assembly have to be draft quality. So if you need really high quality drawings, this might not be the best option.
Okay, so that's something to keep in mind. So we've covered 4 different options for creating connectors: 3D Sketch Connector, Envelope Publisher, Make Multibody, and Local Speed Pack. It sounds like they each have their strengths and weaknesses, and the best one to use really depends on what you're trying to do, how complex your assemblies are, and what version of SOLIDWORKS you have.
Exactly. You've got to choose the right tool for the job. And the presentation actually included a handy table that summarized all 4 techniques and listed the SOLIDWORKS versions they work with, their pros and their cons.
That's helpful.
It is. It really shows that there's no one-size-fits-all solution. The best approach is the one that meets your specific needs.
So these connector techniques are clearly a game changer for team collaboration on big assemblies. But the masterclass also touched on the other 2 critical factors for getting the most speed out of SOLIDWORKS, right?
They did, yeah. While they focused on the user side of things in the collaboration section, they also emphasized how important the hardware is. If you're working with really big assemblies, you absolutely need a computer that can handle it.
So that means a fast processor, lots of RAM, and a good graphics card.
Exactly.
Right.
And it needs to be set up correctly for SOLIDWORKS.
Right. So it's not just about the software, it's about the whole system.
Exactly. And the other big factor is the software itself. Making sure you're using the latest version of SOLIDWORKS and keeping up with all the updates can make a huge difference in performance. Those updates often include bug fixes and improvements that can really speed things up.
It's like giving SOLIDWORKS a tune-up.
Exactly. So while these connector techniques are awesome tools to have in your arsenal, it's important to remember that the best way to maximize your performance is to take a holistic approach. You need to think about your hardware, your software, and how you're actually using SOLIDWORKS.
It's about the big picture.
Exactly.
Well, this has been a fantastic deep dive into how to work faster and smarter in SOLIDWORKS, especially when you're dealing with large assemblies and teams. We've learned about all the things that can slow you down, and more importantly, we've got some practical techniques that you can start using right away to make your life easier.
We have, and I hope people will try out some of these techniques. I think they'll be surprised by how much of a difference they can make.
I agree. So now that you've got all this knowledge, think about how you can use it to improve your next big SOLIDWORKS project. Remember all those potential bottlenecks we talked about at the beginning? Which ones do you feel like you can tackle now that you know about these connector techniques?